All right, this is homework 22. The first problem says find the Maclaurin polynomial. So that means center 0 of degree n for the function. So, all right, our first problem, I will warn you right off the bat, is a bit irritating because we're going to have to use product rule to find our derivatives. But knowing that this is the worst one, we'll just get it out of the way. So if you want to begin by reminding yourself how to build one of these Maclaurin polynomials, we've got to get out to the fourth order. So that means we're going to have to find f of 0 plus f prime of 0 plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus the fourth derivative evaluated at 0 times x to the fourth over 4 factorial. So this is what we're going for. We need to find these values. So let's start with f of x is x squared times e to the negative x. And we want to find f of 0. So that comes out to 0. F prime x, I need to use product rule here. So x squared, so first times derivative of the second, plus second times derivative of the first. Now I need to plug 0 into this, but because I'm going to also have to take the derivative of this, rather than doing product rule plus another product rule, if I factor this a little bit, I'll just have one product rule to look at. So I know the GCF is x times e to the negative x, but I'm just to simplify the derivative piece of it, I'm just going to factor out e to the negative x, or I could do the negative version of that, doesn't matter. And then I'm just going to write down what I would have left, because I'll be left with something algebraic out here. So if I take out e to the negative x, I'm going to put the positive term first. So this term would be left with 2x. This term would be minus x squared. So this will be easier to take the derivative of when I'm finished. It's also pretty easy to plug 0 into. So when I plug 0 into here, I get e to the 0 times 0. So that also comes out to 0. So the first two terms are 0 here. All right, so then let's take the second derivative. So first times derivative of the second plus second times derivative of the first. Again, I'm just going to factor out not the GCF, but just an e to the negative x. And you could do more than that if you wanted. I just don't want to. So this is going to be, because it'll just give me one product rule if I do it like this. So this is going to be 2 minus 2x will be left. And then careful here, you have a negative here that would have to get distributed through the 2x minus x squared that's left. And I'm going to clean that up before I plug anything into it or work with it further. So we've got a 2 here that will stay. Negative 2x minus 2x is minus 4x, and this becomes plus x squared. So that's the f double prime equation. Now plug 0 into that. This is our first non-zero term because we get e to the 0, and then we do get 2 here. So 2 times 1 is 2. All right, we have to do this 2 more times. So the third derivative is again first times derivative of the second plus second times derivative of the first. Let's take a minute to get our negative e to the negative x out. So that just leaves me with negative 4 plus 2x. And then again, this minus will get distributed through these parentheses that are left. Let's clean that up before we plug anything into it. Negative 4 minus 2 will be negative 6. 2x plus 4x will be plus 6x. And again, we have a minus x squared. So that's the triple prime equation. When we plug 0 into that, we get 1 times negative 6. So negative 6. We need to do this one more time. First times derivative of the second plus second times derivative of the first. I'm still going to factor out because I think I don't want to mess up my math on this. I trust my factoring more than my plugging a number in and seeing if I get it right skills. So this is 6 minus 2x minus parentheses negative 6 plus 6x minus x squared. But you certainly could plug in 0 here and get the same answer. All right, so what is f4 of 0? So e to the 0 is 1. And then what is all of this? This is 6 plus 6 is 12 minus 8x plus x squared. So yeah, when you plug in 0, you're just going to be left with 12. All right. That's everything we need to write this fourth order polynomial. So we're saying that x squared e to the negative x can be approximated by, so you can put in the zeros if you want. And this should have had an x right here. I missed that. Sorry. So 0 plus 0x, and then plus 2x squared over 2 factorial. You could simplify that or not. Minus 6x cubed over 3 factorial. That also simplifies. Plus 12x to the fourth over 4 factorial. 4 factorial is 24, so you could reduce that as well. But remember, you don't have to reduce them, so I'm not going to bother. I'm just going to leave it unsimplified. I don't want to make a silly mistake reducing and then not get points for part of the answer. All right, number 42. Approximate the function at the given value of x using the polynomial found in 20. So we did all of that to help us with problem 42 as well. So, all right, so I'm going to take this answer and try to copy it. All right, so here's what we had. I just don't want to keep scrolling up and down. All right, so here's what we had. And yeah, we're just supposed to plug 1/5 into that. So f of 1/5 or 0.2 will be easier for me to type on my calculator. So let me split screen this with my calculator. All right, so plugging in 0.2, I'm going to ignore the 0 terms. Maybe I will simplify this. That would be easier to type in. This is really just x squared minus x cubed plus 1/2 x to the fourth, right? 12 over 24. All right, so 0.2 squared minus 0.2 to the third plus 0.2 to the fourth divided by 2. Getting 0.0328. I have a slightly different answer from, I'm trying to decide if I typed it in incorrectly the first time I did it or what. Let's see what 0.2 to the second times e to the negative 0.2. Okay. Yeah, the answer I had on my first key looks farther off than the one I just got. So I bet I had a typo the first time I did it. This looks right to me. So 0.0328. It's a good idea to, if you think you made a mistake, compare with what the actual answer should be. This is f of 0.2 in actuality. So we're just looking at like how far off it is. It's pretty close. My first answer was 0.03205. I bet I just had a typo somewhere. All right, let's go on to this one. Use Taylor's theorem to obtain an upper bound for the error of the approximation, then calculate the exact value of the error. So it looks like a fourth order polynomial has been used to approximate cosine of 0.3. And it looks like the center is 0 because this just says 0.3 squared. It doesn't say 0.3 plus or minus some other number. All right, so how do I find an error for a P4? So let me kind of set up the formula, because you might see this the way they write this on the AP test. So they might say something like, okay, there's an actual value of cosine of 0.3. And what's the difference between that and our P4 approximation of 0.3? That's equal to some sort of remainder, fourth order remainder at 0.3. And our formula for that is that it's less than or equal to absolute value of the n plus 1th derivative. So remember, we have n, so the 5th derivative in this case, the max value of that, we'll figure that out, times 0.3 minus 0 to the 5th over 5 factorial. The formula is normally n plus 1s, but when you know n, you fill numbers in for those. So what is the value of this error is what they're saying. So the only thing I don't have a number for right now is the 5th derivative. Now, when your function is sine or cosine, in this case it's cosine x, any nth or n plus 1 derivative will either be plus or minus sine x or cosine x. It depends on, where you land. And remember, we've said just blanket statement, because we're going for maximum error. We want to be conservative and say we think we're going to be way off and hope and know that we'll be better. The max is always equal to 1 when your function is sine or cosine. So that's nice, because you don't have to think about things or plug things in. It's when f of x is a natural log or rational or polynomial or something like that we have to consider what the max number is. All right, so there's just a 1 going in for this. So now really this is just 0.3 to the 5th over 5 factorial. And it's in absolute value just so that we're saying we don't know if the difference is actually positive or negative. And I'm just going to type this into my calculator. So 0.3 to the 5th divided by 5 factorial is 120. And so I am getting let me split this, about equal to 0.123422025. Now, what is the actual error? The actual error should be smaller than that. So let's see. The actual error is what I get when I type in cosine of 0.3. That's that answer. Versus what I get when I type in this P4 expression, 1 minus 0.3 to the 2nd. Oh, I have an extra decimal place, extra exponent in there. 1 minus 0.3 to the 2nd divided by 2, that's 2 factorial, plus 0.3 to the 4th, and we're dividing that by 4 factorial, which is 24. They're coming out close. Let's subtract them. It doesn't matter what order you subtract them in. This is the actual error in air quotes because the calculator is rounding this value as well. Let's write out what that is. So let's see. So actual error is equal to negative 0. Not absolute value, sorry. Negative 0.0000. There are 5 zeros here. 10109. 5 zeros here versus 4 zeros here means I thought I was only going to be accurate to 4 decimal places, but actually we're accurate to 5 decimal places. The number of zeros means that's how many places are going to match up until your approximation is different than the actual value. So yes, this is our upper bound. All right, for the next set, it says determine the degree of the Maclaurin polynomial, again, C is 0, required for the error in the approximation of the function at the indicated value to be less than 0.001. All right, so let's set this up. So they're asking me about an error, and I don't know the n. So the distance from the actual value of sine of 0.3 minus whatever order polynomial I approximate at 0.3, that's equal to the remainder at 0.3. And the formula for that is less than or equal to the n plus 1th derivative at z, we will determine that max value off to the side in a minute, times x minus c. So x is the approximation you're plugging in. C is the center, raising that to the n plus 1, over the n plus 1 factorial. And we want to keep this less than 0.001. So setting this up again, I talked about this earlier in the homework. The function is sine x. Any derivative you take will end up being sine x or cosine x, maybe plus or minus. And the absolute max, even if we don't really hit that between 0.3 and 0, the actual max is 1. Because again, we're going above and beyond how far we actually think we're going to be off. Like, I'm saying I'm going to miss by 1 foot just to be conservative, when I really am going to miss by like a third of a foot or something like that. Okay, so we're putting a 1 in for that. 3/10. This is 3/10 to the n plus 1 over n plus 1 factorial. Why did I change that to 3/10? I only think about that if I'm worried that it's going to be a non-calculator problem, or like, how would I do this if it were non-calculator? You do need to know, maybe not for this particular problem. This would probably be a calculator one, but you do need to know how to manipulate this a little bit to turn it around just to see if things are working out. So you would be plugging and chugging to see how many n's is it going to take. It's not going to take a lot for 10 to the n plus 1 times n plus 1 factorial over 3 to the n plus 1. How many n's will it take for that to be a number bigger than 1,000? So if you're just kind of plugging and chugging, you might say, okay, I'm going to start with 1, even though the answer is never usually 1. That would make this 10 squared times 2 factorial over 3 squared. 100 times 2 is 200 over 9. That's definitely not bigger than 1,000. Okay, try 2. 10 to the third. Wait, if I plug in 2. Oh yeah, 10 to the third, that's 1,000. Multiply it by 6. But then you're going to divide it by 27. So what do we do? So 6 over 27, that reduces, right? You can reduce by 3. It's 2 over 9. So that is 1,000. That is 2,000. But you're dividing it by 9. Is that bigger than 1,000? I don't think so. You can divide it out to double check. We're still less than 1,000. Okay. What about 3? 10 to the fourth times 4 factorial over 3 to the fourth. 10,000 times 24 is 24 with 4 zeros. 240,000 divided by 81. Now, I could do this division and try to figure this out, or I could think about it this way. If this is 1,000, this just needs to be bigger than 1,000, right? That is the question. Now, 81 over 81 is 1. 8,100 over 81 is 100. 81,000 over 81 is 1,000. And 240,000 is bigger than 81,000. So that's one way for me to reason of like, oh yeah, this is bigger than 1,000 without really having to do the division. N equals 3 is the answer. Now, more likely, this would probably be a calculator one. So remember, if you are allowed to use a calculator, don't run through all that. You do still need to do a bit of rearranging. You want to be able to get this into your calculator. Or you could go back here and type this in and look for the decimal version. But get all this stuff out of here. I could type in 10 to the x plus 1 times x plus 1 factorial. You can do alpha window. There's factorial. Or it's in the math menu, math probability. We're dividing that by 3 to the x plus 1. I don't need parentheses around that because I'm just dividing by one term. And then I'm going to go to my window and have it start at 1 and have it count by ones. And I'm just looking for, how long does it take to get bigger than 1,000? So not long. The third, What's happening? The third term, sorry. There we go. The third term is where the first time we're bigger than 1,000. So that agrees as well. Let me go back and show you. What if you went back here and typed this in? So 3.3 to the x plus 1. Oops, 0.3. Lots of typos today. Sorry. There, divided by x plus 1. I'll show you the other place factorial is. Math, probability, factorial. So here, I would be looking for when do I get something smaller than, and make sure you're in this column, 0.001. So this is 0.0003375. So that's, again, where it's smaller than 1. So if you're allowed to use a calculator, you have options. All right, so my answer is n equals 3. Now with sine and cosine, remember the Maclaurin polynomial for sine is all the odd powers of x. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It keeps going. So what if I got the n had to be 4? If n is 4, that would be like the 0 term. There's a 0 x to the 4th over 4 factorial. So if I got n equals 4, then the degree would still be 3. But because I got n equals 3, that matches up with its term. If I got n equals 2, then the degree would be 1. If I got n equals 6, the degree would be 5. So you go with the degree that's before it if you land on a 0 term for some reason. Okay, and that's only for terms that have 0, like some terms that are 0. Most of the time, the n that you get is the degree. Okay, now this one's kind of strange. I was checking like what the book did and comparing it with my numbers, and they said f of x is just ln x. But if we're trying to do a Maclaurin polynomial and it's centered at 0, I don't think that we can just have ln x be our value. Well, maybe we could. Could we? Well, okay. So if we did, let's see, could we? I don't think so. I think it needs to be ln, I keep talking myself in circles about this, 1 plus x. Because we're centered at 0, and when we plug into our formula, we can't have a 1.25 minus 0. That's going to throw off our formula. So I'm saying this is f of x. And so the center is still 0, but the x that we're trying to evaluate is at 0.25 instead of 1.25. Okay, so what am I talking about? Because they're asking me what is the difference between the natural log of 1.25 and the nth order approximation we're going to do to approximate 1.25. But it's not really 1.25. Like, what are we plugging in for that? 0.25. Because we're adding, in the formula, I'm saying f of x is 1 plus x. Okay, so that's equal to the remainder at 0.25. And that's less than or equal to the n plus 1th derivative at some maximum value z times x minus c, so 0.25 minus 0 to the n plus 1 over n plus 1 factorial. That's supposed to stay less than 0.001. This is what I was saying. You don't want to have 1.25 minus 0 here. It will mess up your answer. It doesn't work out. All right, so, and I really don't think they would have you have to infer that on the AP test. I think they would tell us what the f of x is to start here. Okay, or they would give us a max value to use. Okay, so what about this? So f of x is ln of 1 plus x. So this is one of those functions where the derivative is not always the same thing. And it's not sine or cosine where I can just say the max is 1. So I need to take a few derivatives until I can figure out the pattern. and come up with what the max value would be. So the derivative of ln 1 plus x is 1 over 1 plus x. You don't need to plug anything into it. You're just trying to find a pattern. We're trying to connect the derivative number to the formula here. So the second derivative, because this is x plus 1 to the negative first, it would be negative 1 over 1 plus x squared. That's for n equals 2. For the third derivative, this would be positive 2 over 1 plus x cubed. And the nice thing about 1 plus x is that there's no chain rule needed because the derivative of 1 plus x is 1. I'm going to do a couple more. I think the fourth derivative is going to be negative 6 over 1 plus x to the fourth. And I've done this a few times so I can see it, but if you can't quite see it, it might take about 5 derivatives to get there. This is going to be 24 over 1 plus x to the fifth. So the n that I'm saying is the number of derivative you're taking. Come up with an nth derivative. So the bottom's easy. 1 plus x to the n. What's the top? Do you recognize this list of numbers yet? 24, 6, 2, 1. So it's n minus 1 factorial. 24 is 4 factorial. 6 is 3 factorial. 2 is 2 factorial. 1 is 1 factorial. And 1 is also 0 factorial. We don't care about the signs because remember, this is an absolute value. So I don't care about the plus and minus signs. And then what about the n plus 1 derivative? So that would just be put in n plus 1. So n plus 1 minus 1 becomes n factorial. And 1 plus x gets raised to the n plus 1. Our last job is to figure out the max value. And remember, z is a number sitting between 0 and 0.25. So plugging this in here, remember that goes in for x. So you're saying, well, I could have n factorial over 1 plus 0 to the n plus 1. Or I could have n factorial over 1.25 to the n plus 1. And remember, a larger denominator means a smaller fraction. So really the denominator with the 1 in it is going to be a bigger number overall. So that means that we can just plug in n factorial for this expression here. So n factorial. 0.25 can become 1/4 to the n plus 1 over n plus 1 factorial. And we're trying to keep that less than 1 over 1,000. We've done this a time or two now. N plus 1 factorial is n plus 1 times n factorial. So this n factorial can cancel with this one. And I'm going to bring the 4 down. So 1 over 4 to the n plus 1 times n plus 1 is less than 1 over 1,000. This is a good candidate for a non-calculator problem. So let's do the work on this because you have just a nice couple of numbers to plug in and multiply together. And, it's not going to be non-calculator and n turns out to be like 11. It's going to be like 3 or 2 or 4. So, all right. So to be safe, I'm going to start by plugging in 1. If I plug in 1, I get 4 squared times 2. 32 is definitely not bigger than 1,000. Plug in 2. That becomes 4 to the third, which is 64 times 3. 64 times 3 is, 192. Not bigger than 1,000. Plug in 3. That becomes 4 to the fourth. Now 64 times 4 is 256. And we're going to multiply that by 4. Now that is bigger than 1,000. And there are 2 ways you can show it. You can either multiply it out. 420, 220, 1,024. Or you could say 1,000 is 4 times 250. And this is coming out to 4 times 256. So that's another way sometimes if the math is something I don't feel like doing, sometimes I'll break it up like that. Or you could say, 1,000 is less than 1,024. So either way, we get n equals 3 again for this one. And there are no 0 terms. You can see if you're plugging 0 into all of these x's, you're going to get numbers for all of them, non-zero numbers. So this will also be degree 3. All right, so that was a strange one. Like I said, I don't think that you're going to be expected to know that it's ln of 1 plus x. I think you would be given that information on an AP test. Determine the values of x for which the function can be replaced by the Taylor polynomial if the error cannot exceed 0.001. So this is basically like saying, yeah, what is that margin of error? How far can we stray from the center? Now on this, I can see two things. I can see that e to the x is being approximated by a third order Taylor polynomial, and I can see it's Maclaurin because the center is 0, since these are all just x's and not x minus some other number to a power. So they're asking me to find the error between e to the x, we don't know what we're plugging in, minus a third order polynomial. That's equal to the remainder of a third order polynomial at some x. And what is our formula for that? It's the n plus 1, so the fourth derivative in this case of z. And we would multiply it by x minus 0 to the fourth. Normally we have a number to put in for x, but that's what we're finding out right now. And it would be over 4 factorial. And we're trying to keep this error less than 0.001. We still need to think about a formula for what is that fourth derivative. So now we can also just find the fourth derivative, but f of x is e to the x. So remember, f prime will just be e to the x, and so will all the derivatives. So f to the fourth derivative of x will be e to the x. And what are our choices for x? That's kind of what we're trying to figure out, right? But if we're thinking about this, it does say that x is less than 0. So we do still need to consider a max. Z is between 0 and the center and x. And if x is negative, it means x would be less than z, which would be less than 0. So we could either have e to the x, and if x is negative, that's going to be like 1 over e to the x every time, no matter what x is, versus e to the 0, which is equal to 1. Now 1 over e to the x, because we know x is a negative exponent, that will be less than 1. So the max value here is 1. So I'm going to plug 1 into that. That means this is just x to the fourth. 1 times x to the fourth over 4 factorial, which is 24. And that needs to stay less than 1 over 1,000. I need to solve for x, so I don't want to flip everything around. I want to say, okay, that means x to the fourth should be less than 24 over 1,000. Now, you could use a calculator for this, or if it's non-calc, you could leave it like this, or you could reduce it. Let's see, are these both divisible by 8, I think? It's 1,000 divisible by 8. I should probably know this. Yeah. Oh, it's 125. Okay, so it's 3 over 125. That's totally optional. Don't have to do that. Now be careful with this. When we are solving polynomial inequalities, we would need to fourth root both sides. But remember, when you fourth root a variable, you get absolute value, x. And this isn't going to simplify much, so I'm just going to leave it like that. And then really, you can take the x out of the absolute value. We've been doing this with with some of our geometric series. This means that x can be anything between the negative fourth root of 3 over 125 and the positive fourth root of 3 over 125. So x could be anything between there, and we would get this thing to converge. But there is one extra little caveat. Remember, it said x is less than 0. So actually, I have to cut it off at 0. X can be anything between the negative fourth root of 3 over 125 and 0. Now, if you had a calculator, I would not go through all the 3 over 25 stuff. I would have said, what is 24 over 1,000 to the 1/4 instead of finding the nth root in my calculator? That's the decimal version of this. So anything between negative 0.393, etc., and 0 is a valid answer. Anything outside of that range will be off by more than 0.001. So that's more error than we're willing to risk for that problem. Okay, this is going to be very similar because the same requirements, we want our error to be less than 0.001, and this is still a degree 3, or a third order, I should say, centered at 0 polynomial. So this is saying we want to know what x values make the error bound between sine x and your third order approximation at x, which is really just the remainder, the remainder of that third order polynomial, less than or equal to, again, we're getting fourth order here, times x minus 0, excuse me, to the fourth over 4 factorial. We still want it less than 0.001. The reason this is almost the same problem is because f of x is sine. And we just said if we have sine or cosine x, the max derivative will be 1. So I'm going to get right back to saying, okay, put a 1 in here. I have x to the fourth over 4 factorial, and I need that to be less than 1 over 1,000. So the only difference between this problem and what I just did is this problem doesn't say anything about x having to be less than 0, whereas this problem did right here, said that. So when I got this answer before, I don't have to adjust it and make it 0 on the one end. That is my answer to this one too. So x to the fourth is less than 0.024. If I fourth root that, I get an absolute value of x is less than the fourth root of 0.024. Oh, my pen just ran out. Hold on. And then you have to know to make that between positive and negative. So my answer is negative fourth root of 0.024 to positive fourth root of 0.024. And I'm not including that value because, let me look at the wording again. Cannot exceed 0.001. I guess maybe it could be less than or equal to, but I always set these up as less than. And they usually don't use that phrasing on the AP test. It will say less than. It will say just the words less than 0.001. All right, that finishes a fairly long homework assignment for so few problems. So number 22 is finished. Please let me know if you have questions on this stuff or want more practice.